Welcome to AI Frontiers, where cutting-edge research meets real-world innovation. Today, we're exploring the robotics revolution through 18 groundbreaking papers from Computer Science Robotics, all published on September 2, 2025. These aren't just academic exercises. They're blueprints for robots that will soon work alongside us in construction sites, navigate our homes as assistants, and explore other planets. Picture this scenario. A robot on Mars, operating millions of miles from Earth, suddenly encounters an unexpected rock formation that could contain signs of ancient life. In that critical moment, with no human controller to guide it, the robot must make an autonomous decision, investigate further, or continue its planned mission. This isn't science fiction. This is the reality that researchers are building today, where machines must navigate complex decisions in environments far beyond human reach. To understand these advances, we must first explore what computer science robotics truly means. Think of it as the brain behind the robot's body. While mechanical engineers design joints and motors that make robots move, and electrical engineers create the circuits that power them, computer science robotics focuses on the intelligence that transforms mechanical hardware into thinking, reasoning agents. It's the fundamental difference between a sophisticated puppet and a truly autonomous partner that can perceive, plan, and adapt. Imagine robotics as a symphony orchestra. The mechanical components are like individual instruments: violins, trumpets, drums, each capable of producing sound but requiring direction. Computer science robotics serves as the conductor, the sheet music, and the composer, all combined into one. It coordinates perception systems that act as the robot's eyes and ears, planning algorithms that serve as its strategic mind, control systems that function as its motor skills, and learning mechanisms that enable continuous improvement over time. This field uniquely thrives at the intersection of artificial intelligence, computer vision, machine learning, and human-computer interaction. Our first major research theme focuses on multi-modal perception and sensor fusion, essentially teaching robots to understand their world through multiple senses simultaneously, just like humans do. Consider how you recognize a friend approaching from behind. You might hear their distinctive footsteps, catch a glimpse of their familiar jacket, or detect their subtle cologne. Your brain seamlessly combines these sensory inputs to reach a confident conclusion. Modern robots are learning similar integration of visual, tactile, thermal, and radar data. One remarkable achievement involves an anthropomorphic hand system that integrates tactile, proprioceptive, and thermal signals through neuromorphic processing, achieving an impressive 97.14% accuracy in object recognition through touch alone. The second transformative theme involves integrating large language models into robotic systems, representing a fundamental shift from programmed behaviors toward natural language interaction. This is like teaching robots to understand conversations rather than just commands. Traditional robots required precise programming for each task, similar to writing detailed instructions for every possible scenario. Modern language-integrated robots can learn from casual conversation, adapting to new situations based on natural human communication. One striking example involves construction robots learning complex tasks through crowdsourced natural language instructions, where workers simply explain procedures in everyday language rather than requiring expert programmers to code every construction operation. Generalization and transfer learning represents our third critical theme, addressing one of robotics' most persistent challenges: creating systems that work beyond their training environments. Imagine training a person to drive only in perfect sunny weather, then expecting them to navigate through snowstorms on winding mountain paths. Traditional robotic systems face similar limitations. However, one ambitious research project tackled this challenge by training a single policy to control 50 different legged robots through extreme embodiment randomization during training. The remarkable result? A universal controller that can adapt to previously unseen robot morphologies with zero additional training, fundamentally challenging the traditional approach of developing specialized controllers for each robot platform. Now let's explore 6 revolutionary breakthroughs that are reshaping the field. First, researchers achieved simulation-to-real transfer without domain adaptation. by developing camera depth models that transform noisy sensor data into clean, simulation-quality information. Second, universal locomotion across diverse robot morphologies demonstrates that a single neural network policy can control 50 different legged robots. Third, neuromorphic sensing for robotic manipulation achieves remarkable object recognition through bio-inspired processing. Fourth, language-guided cloth folding integrates large language model planning with vision language model perception. Fifth, radar-based perception enables robust operation in harsh environments where optical sensors fail. Sixth, enhanced security frameworks protect LLM-integrated robotic systems from prompt injection attacks while improving operational safety. For our paper of the day, let's examine the fascinating work on generalizable skill learning for construction robots by you and colleagues. This research addresses a fundamental paradox that has limited robotics adoption in construction for decades. Construction work presents seemingly perfect conditions for automation. Many tasks are repetitive and well-defined. However, construction environments are highly variable, with each project presenting unique challenges, materials, and spatial configurations. The core problem wasn't just technical, but also social and economic. Construction companies couldn't justify hiring robotics experts for each project, while construction workers lacked programming backgrounds despite their deep expertise in building techniques. You and colleagues developed an elegant solution through natural language instruction that bridges this expertise gap. Their framework allows construction workers to teach robots complex tasks simply by describing them in everyday language, just as they might explain procedures to new human workers. But the innovation extends beyond language processing. The researchers developed a standardized, modularized, hierarchical modeling approach that represents skills as composable modules. Think Lego blocks, where individual skills like pick up drywall sheet, align with wall studs, and secure with screws can be combined to create complete installation procedures. Building information modeling, integration provides semantic understanding, enabling robots to recognize load-bearing walls versus partitions and plan accordingly for safety compliance. What makes this construction robotics work particularly significant is its potential to democratize the field. Instead of requiring expensive reprogramming for each task, construction companies could deploy robots that learn continuously from human workers. This approach addresses automation displacement concerns by creating new roles where experienced workers become robot trainers and supervisors, extending their expertise across multiple job sites simultaneously. Rather than replacing human knowledge, the system captures and amplifies it through robotic systems that understand natural conversation. The experimental validation on drywall installation using full-scale industrial manipulators demonstrates practical viability for this revolutionary approach. Looking toward the future, we can envision robotics evolution like a garden ecosystem transformation. Traditional robots resembled carefully cultivated flowers in controlled greenhouse environments, beautiful and functional, but requiring precise conditions and constant maintenance. The robots emerging from current research are more like hardy wildflowers that thrive in diverse environments, adapt to changing conditions, and support other systems around them. They're becoming genuine partners in human endeavors rather than sophisticated tools. The convergence of multi-modal perception, language integration, and learning algorithms suggests we're approaching a critical tipping point where robots can truly understand and respond to real-world complexity. The trajectory we've explored today points toward robots as genuine collaborators across diverse applications, from Mars helicopters making autonomous scientific discoveries to construction crews learning through conversation, from soft hands that feel the world through neuromorphic touch to universal controllers that adapt to any robot morphology. We're witnessing the emergence of truly intelligent machines. These advances prioritize safety, security, and human collaboration, suggesting that the robotics community is maturing toward deployment-ready systems that work safely alongside humans in real-world environments, rather than pursuing technological capability for its own sake. The research synthesis we've explored represents thousands of hours of dedicated work by brilliant minds worldwide, each contributing essential pieces to the grand puzzle of artificial intelligence and robotics. However, the story extends beyond academic papers to implementation, deployment, and real-world impact. These technologies are actively transforming industries from healthcare to space exploration, creating new possibilities for human-robot collaboration that seemed impossible just years ago. The emphasis on natural language interaction, adaptive learning, and safety-conscious design suggests we're entering an era where robots become intuitive partners rather than complex tools, requiring specialized expertise. This analysis was synthesized using GPT and Claude Sonnet-4-20250514 for content processing, with TTS synthesis via Deepgram technology and image generation through OpenAI systems. Human expert review ensures accuracy, though some oversights may exist. References are provided for verification. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprint server.